Hello and welcome to today's lecture. In the last few lectures, we had discussed how to collect data, how to represent data and how to come up with useful statistical metrics of quantifying your data. Okay. And we also had a brief session on how to fit data depending on the nature of the curve. So, we have completed the first section of statistics, which is descriptive statistics, and it brings us to our second section, which is interferential statistics. That is, given a sample that you have collected, you want to predict something about the whole population, okay? And that brings us to discussing one of the most important tools of statistics, which is probability. Okay? So, if we think of why probability might be important, let us say you have collected the distribution of scores. Okay? So, this is exam marks and this is your frequency, okay? And let us just say this is how your distribution looks like. Okay? So, and let us say this is 10 out of 100 and the maximum is 90. Okay? So, so this is, let us just say that you have collected the statistics not from the whole class, but you have asked this from the students who were present in a given day after the exam was over. Okay. So, this is a sample. So, let us assume that out of 100 total students, so n is 100, you have sample n is equal to 40 and this is the distribution that you get. So, based on this you can ask questions like, what is the chance that someone has scored 100 versus 30 versus 20, so on and so forth. Okay. So, let us take another example of that of a coin toss. Okay. You want to understand whether a coin is biased or unbiased. By unbiased, I mean that when you flip a coin, on an average you would expect to get a tail or a head almost in equal proportion. That means, the chance or the probability of a head occurring should be nearly equal to the probability of a tail occurring, which is equal to half. But if you were to do that experiment only thrice, that means you flip the coin 3 times, or 4 times, right? Is there a chance that you will always get 2 out of 2 and you increase the sample size? If you then do it for 10 times, let us say. So, if you do it only 4 times, it is possible that you might have 3 heads and a tail or the other way around. Okay? But if you do it 10 times, right, and let us say all 10 times you are getting a head and not a tail under any conditions, you are reasonably sure that the coin is not unbiased, but biased. Okay? So, probability is the tool which helps us to come up with computing chances or saying something about the population given a small sample. Okay? So, when we come to probability, we begin by definition of few terms. Okay? One is, what is my sample, okay, or sample space. Okay. So, so when you toss a coin, let us say, there are 2 possibilities, okay, or 2 outcomes possible. Either you have a head or you have a tail. Okay. So, the sample space is, so it basically represents the set of all possible outcomes. Okay. So, in case of tossing a coin, my sample space is typically written as S, is nothing but a head appearing, H is short form for a head, or a tail appearing, T is short form for a tail. Okay. So, now imagine you roll a dice. Okay. So, our dice has 6 sides. Okay. So, when you roll a dice, it is possible that you will get a 1, you can get a 2, you can get a 3, a 4, a 5 or 6. So, there are in essence 6 outcomes. Okay. So, you will write the sample space for rolling a die as the number 1 appearing, the number 2 appearing, the number 3 appearing, the number 4 appearing, the number 5 appearing and the number 6 appearing. So, this is your sample space. Okay. So, this is the entire sample space. Now, let us say I say sample space S represents all natural numbers. Okay. So, my sample space, all natural numbers are positive numbers, okay, greater than 0. Okay. So, my sample space will represent 1, 2 dot 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 infinity. In other words, there are infinite possible outcomes which dictate. So, this is sample space is space of all natural numbers. Okay. Or let us say you can think of the dosage you can administer to a patient with a certain drug. Okay. In that case also S has infinite possibilities, right. You can give 500 milligrams, 100 milligrams, 105 milligrams, so on and so forth. So, there are really infinite possibilities here. So, a sample space can be infinite or can be finite, as in case of a rolling of a die or tossing a coin. Okay. So, S is the list of all possible outcomes. Now, let us say in case of a coin toss problem, you can define something of interest to you is when a head appears. So, you can call E is short form for an event, okay, which is associated with one particular outcome. So, in that case my event can be simply H, or so I can write this as E1 and I can write this the another event E2 as a tail appearing. Okay. Now, let us go to the example of rolling a dice. Okay. So, I can, depending on the type of event that I want to define, let us say, so I have a rolling a die. Okay. I say event E1 is the event that a number less than 3 appears. Okay. Less than 3 appears. So, in that case, so for rolling of a dice, my sample space S is 1, 2, 3, 4, 5, 6. Okay. My event E1 is then a number that less than 3 appears. So, I only have event, there are 2 possibilities, either you have a 1 or a 2 appearing. Okay. So, what you see, so always event, the number of possibilities in generally an event can be less or equal to the number of possibilities in case of a sample. Okay. So, when I have, so in the general case for any event E, the number of possibilities of E is less or equal to the number of possibilities in the sample space S. So, this is my sample, okay, and this is my event. So, n is the number of possibilities. Now, given two events, let us say E1 and E2, I can think of an event which is represented by E1 union E2. Okay. So, this would be read as E1 union E2. Okay. So, this is interpreted is either E1 or E2 or both occur. Okay. So, this is a union event, let us say E3 I have defined as the union of E1 and E2. It is either E1 or E2 or both occur. Okay. So, when you, or I can have another event E4 which is written as E1 E2. So, this is read as E1 intersection, okay, E2, which means either E1, no. So, this means both E1 and E2 occur. Okay. So, the possibility that both E1 and E2 are occurring. So, in the case of rolling of a dice, let us say if I define my E1 as the set of all odd numbers appearing. So, in that case it will be 1 3 5 and E2 is the set of all numbers less than 4 1 2 3 4. Okay. So, basically numbers 4 or less occur, and this is odd number occurs. So, you see there are few entries which are common to E1 and E2 like 1 and 3. There are some other entries which are present in E1 like 5 which does not appear in E2 and vice versa. Similarly, the numbers 2 and 4 appear in E2, but not in E1. Okay. So, that means, so it gives me it gives you a clue that depending on how you define an event, you can have multiple possibilities and there might be overlap as in this case, or let us say if I define the number an event E3 is the highest number appears. So, which is nothing but 6. Okay. So, in this case there is nothing in common between E2 and E3 or E1 and E3. Okay. So, one of the easy ways of representing these phenomena is by using Venn diagrams. Okay. So, you can generally represent the whole sample space by a rectangular block. So, this is my S. Okay. I can represent an event E1 like this by a circle. So, this conveys the message that E1 is a subset of S. So, E1 when E1 is fully contained in S. So, we write that E1 is a subset of S. Okay. So, I can also write this particular expression. Okay. So, this amounts to writing this term mathematically. Okay. So, I can represent an event E1, I can represent another event E2 and I can represent another event E3 here. Okay. So, what were my previous events in the case of rolling a die? E1 is 1 3 5 occurring, E2 is 1 2 3 or 4 occurring, and E3 is 6 occurring. So, note the way I have drawn all of these events E1, E2 and E3 are represented as circles within this rectangle, which means all these events that I have drawn fulfill this particular criteria. Okay. All are contained within the sample space. Okay. Another important measure, so the way I have drawn E1 and E2, I have drawn with them some overlap between the events E1 and E2. Okay. But when I have drawn E3, I have drawn it outside of E1 and E2. Okay. This gives you the idea of, so what I can say is when E3 occurs, so the when number 6 occurs, I can say clearly that neither event E1 or nor event E2 have occurred. Okay. So, this is a case when I can say that events E1 or EI and EJ are mutually exclusive. Okay. When EI intersection EJ is equal to phi. Okay. This is null. There is nothing in common shared between the events E3 and E2 or E3 and ER. So, I can write E1 intersection E2 E3 is equal to null and E2 intersection E3 is equal to null. Okay. So, there is nothing in common between E1 and E3 or E2 and E3. Okay. So, now let us again go back to the sample space. You have E1 here, E2 here, here and E3 here, and this is your whole sample space. Okay. So, let me divide this into 3 segments. Okay. I divide them into 3 segments labeled as 1, 2 and 3. So, what does the zone 1 implicate? Zone 1, E1 has occurred, but E3 has not occurred. Okay. The event 2 is both E1 and E2 have occurred. Okay. And similarly, the event 3 like 1, E2 has occurred, but E1 has not occurred. Okay. So, using the concepts of union or intersection, I can write 1 is E1. Okay. So, it is E1 is the whole event. So, 1 is simply E1 minus the area 2. Okay. Let us find out what is the area 2. Okay. Area 2 is nothing but E1 intersection E2. Okay. And so, area 1 becomes E1 minus E1 intersection E2. Okay. Similarly, the area 3 becomes E2 minus E1 intersection E2. Okay. So, I can write down in the most general case. Okay. In the most general case, if I draw true events where there is overlap, okay, let us say this is my event, this is my event E2. Okay. So, probability of E is generally this designates the probability of event E occurring. Okay. So, probability of E1 union E2 is given by the expression probability of E1 plus probability of E2 minus probability of E1 intersection E2. Okay. So, let us see how we can get this expression. Okay. We can use the earlier step, right. Okay. So, we again break it down as before into 3 segments 1, 2, 3. Your area 1 is E1 minus E1 intersection E2. Okay. So, 2 is E1 intersection E2 and 3 is E2 minus E1 intersection E2. Okay. So, if I calculate the probabilities, okay, if I calculate the probabilities and add them up, so I can write probability of event 1 is equal to probability of E1 minus probability of E1 intersection E2. Okay. Probability of 2 is equal to probability of E1 intersection E2, and probability of 3 is probability of E2 minus probability of E1 intersection E2. Okay. So, if I add these 3 up, you have 2 negatives and one of them which is a positive, one of them will cancel each other, you will have P1 Pe1 plus Pe2 minus Pe1 intersection E2. Okay. So, this is how you can compute the probabilities of composite events depending on how the events are defined. Okay, this is slide 7. Okay. Now, if you have an event A, let us say, which is here, this is my sample space. So, what is the chance of A not occurring? So, this is called the complement of A, and this event. So, event of A not occurring A not occurring is denoted by A complement or A bar, as the case may be. Okay. So, the probability of A not occurring is this area under the curve. All these possibilities are when A does not occur. This is when A occurs. So, I can write, so I can clearly see. So, it brings us to the concepts of axioms of probability. So, when you have these two events, so of course, A and A complement, A and A complement are mutually exclusive. Okay. A and A complement are mutually exclusive. Okay. So, logically speaking, so what is the chance of probability of a sample occurring? Okay. So, sample is the list of all possible events. Okay. So, clearly, so I can say probability of S, okay, it brings us to the chance that probability of S is equal to 1. If S is the list of all possible outcomes, then chance that S will occur is 100%. So, that is why you write the expression probability of S is equal to 1. In the generic case, so then the probability of an event E must fulfill one particular criteria, first of all, which I can say 0 less is equal to probability of an event E less equal to 1. So, in the case when your event is just a sample itself, then your probability of the event is equal to 1, that is the highest bound. If you define an event where it does not occur under any case, then 0 is the probability. So, in the case of when S is the least sample size of all natural numbers, and you ask what is the chance that the number -5 will occur. So, because -5 is not there in the sample at all conditions, so you will have that probability to be 0. But in this case, so this case which we drew, probability of A is dividing this area by the total area, you will get a fraction, and hence this criteria is going to be solved. Okay. So, one axiom is probability of the sample space is equal to 1. The second axiom is probability of S is basically any event E is less equal to 1 and is also greater equal to 0. Okay. So, I can write for events which are mutually exclusive. So, let us say E1, E2, E3 are mutually exclusive. Okay. So, in this case, how will I represent E1, E2, E3 in this? If they are mutually exclusive, so this is my event E1, this is my event E2, this is my event E3. So, for these events which are mutually exclusive, I can write down the expression what is the chance of probability of E1 union E2 union E3. It is nothing but the summation of probability of the event EI. Because there is no overlap, so as we discussed, you have this particular expression, So, when E1 and E2 are mutually exclusive, then the area of the zone 2 reduces to 0. So, the probability of E1 intersection E2 is 0. So, as a consequence, you will have E1 union E2 is equal to probability of E1 plus probability of E2. Okay. So, in case of exclusive events, I can write this particular expression. Okay. So, the next thing I can write for A and A complement, I can then write probability of A plus probability of A complement, which are mutually exclusive. So, these events are mutually exclusive, but together they span the entire sample. So, this is nothing but the probability of the sample space itself is equal to 1. So, I can write probability of A complement is equal to 1 minus probability of A. Okay. So goes the few formula that we have derived. Let us take a specific example, okay, the rolling of a dice. So, my sample space is 1, 2, 3, 4, 5, 6. Let us say my event E1 is the set of all even numbers. So, that will have 2, 4, 6. The set of E2 is the set of all odd numbers, which is 1, 3, 5, and so these are 2 events. So, I can clearly see that E1 intersection E2 is equal to 5. There is no number which is common in these 2 events. Okay. So, I can write probability of E1 intersection E2 is equal to 0, because these are mutually exclusive. So, they are mutually exclusive. Okay. Probability of the event E1 occurring. So, probability of event E1 occurring. So, there are 3 possibilities, which is 3, and the total number of possibilities is 6. So, probability of E1 occurring is going to be half, and this is same as the probability of the event E2. Okay. So, probability of E1 plus E2 union E2, because these are mutually exclusive, is simply P of E1 plus P of E2 is equal to 1. Okay. So, we have in essence confirmed this expression, that probability of A and probability of A complement is equal to 1. With that, I stop our lecture today. So, what we have briefly discussed about the need for probability and some of the basic axioms of probability, and how you can use Venn diagrams for describing events visually, so you can understand what is what. Okay. With that, I thank you for today's lecture, and we look forward to our next lecture. Thank you.